Okay, so very quickly, some motivations. I was expecting to be a lucky guy, and that Arthur would have been the previous speaker, so that I could go quickly through the motivations and the background. But anyway, let me explain briefly the context of this work. So what we want to do is to explain predictions, okay, achieved by classifiers of any kinds. And the following quite a recent research line in our work, what we do is to delegate the work to a Boolean circuit. So we start with a classifier, and then we're using a specific encoding depending on the nature of the classifier. We generate a Boolean representation in a given language, L. Okay, and the point is that what we want to do is to get a Boolean circuit that exhibits precisely the same input-output behavior as the classifier. Okay, so this is basically the assumption. And in this research line, what we have done in this work was to identify a number of XAI queries of interest. I'm going to list some of them, showing how they can be addressed by combining properties of Boolean functions, properties known as queries and transformations, okay, that makes sense for Boolean functions, okay, viewed as an abstract data type. So not assuming any specific representations of the Boolean function. Okay, and they have nothing to do as well with respect to classification issues. Okay, and the next step and the results actually of this work are a number of sufficient conditions, okay, using those queries and transformations, so sufficient conditions on the representation languages, such that when they hold, okay, the XAI queries we considered can be solved efficiently. We have tractable algorithms to address those queries. And finally, exploiting previous results, especially from the knowledge compilation map, we can point out a number of knowledge compilation languages satisfying those conditions. Okay? So the formal setting very quickly, we start with a discrete multi-label Boolean classifier of any kind. Such classifier actually maps a vector or any vector of Boolean features to a vector of Boolean classes, okay? And we suppose that the classifier has been learned, and then we suppose also that it is associated with a Boolean circuit, okay, of any kind, having the same input-output behavior, okay? An important point, of course, to note is that this assumption is not makes sense. There exists already a number of encodings mapping such classifiers to Boolean circuit. Actually, I guess that in Arthur's talk next, you will see such an encoding for specific binary neural networks. But let me here to illustrate this idea, just consider a toy example and another family of classifier, namely random forest. So this is a toy example. We consider just 3 Boolean features. We want to recognize fruits. Actually, we have 3 types of fruits: grapefruit, banana, apple, and we want to recognize them based on Boolean features, the fact that they have sweet taste, they are green or not, the color, and they have a shape that is round or not. Okay? A random forest is simply a collection, a set of decision trees. Here you have 3 decision trees. If you want to classify any instance using a decision tree, you have to follow the unique compatible path in the tree, okay, from the root up to the corresponding leaf. So for instance, if you know that the instance at hand is not sweet and not green, then it will be classified as a grapefruit by the first decision tree here. Okay, and then what add a random forest? Just majority voting, a form of voting, in order to get classifiers that are more robust to noise. Okay, so you are going to classify here an instance in a given class only if a majority, here at least 2 classifiers, are going to classify this instance in that class. Okay, how to encode those kind of classifiers? Let me briefly show that. It is quite simple. In fact, what you're going to do is to consider additional Boolean variables, okay, intermediate variables Z. You're going to consider one variable per class plus one variable per class and decision tree. And the first thing you have to do is to encode the decision tree. Okay, so let's consider the first decision tree here, T1. Okay, and let's focus on a specific class, for instance, the grapefruit. Okay, when is a given instance recognized as a grapefruit using this decision tree? It is quite easy to determine it. You just look at the leaves of the decision tree that are labeled by grapefruit. Okay, you have two leaves here of this kind, and you consider the path here leading to those leaves. Okay, so the first path here is the one I presented just before. The fruit is not sweet and not green. You conclude it is a grapefruit. And you have an additional path here. If now the fruit is sweet and green, it is considered, it is recognized as a grapefruit, okay, by the classifier given here. Okay, and then you introduce an additional variable, grapefruit, in the sense of decision tree 1 here. When is an instance recognized as a grapefruit by this tree? Precisely when, okay, so you have if and only if here. You have the two paths here, the two terms corresponding to the path. It is not sweet and not green, or it is sweet and green. Okay, and then what you have to do next, in order to go from decision trees, to random forest, just adding majority voting for each class. Okay, the object, the instance considered at start is considered as a grapefruit precisely when a majority of decision trees, so at least two decision trees over three, okay, recognize it as a grapefruit. Okay, so this is a pseudo-Boolean constraint, cardinality constraint, in fact, here. And in fact, what you get then is a Boolean circuit. Okay, when you just remove, you forget every variable from Z, okay, you can get a projection of this Boolean circuit that can be actually represented as a truth table. The truth table is here, okay. To every combination of Boolean values corresponding to the features, you have the corresponding classes. Okay, and now, of course, we are happy with this Boolean representations because we know a lot about Boolean circuits and Boolean representation. We can do many things, many reasoning tasks, especially useful for explaining or verifying classification circuits. So what we have done in this work is to first identify a number of queries that can be split into two categories: explanation queries on the one hand. So those queries are specific to an instance you want to classify. Okay, you want to explain why this instance, for instance, has been classified in a given class. Okay, so there are a number of queries that can be viewed as explanation queries, or about local explanation in some sense. I will focus, of course, I do not have enough time to enter into the details of all those queries. I will show you more details about one of them, enumerating counterfactual explanations. I will explain this one. And we have also identified a number of verification queries. So verification queries are not specific to an instance to be classified. They are about the classifier as a whole, okay? And often we have some prior knowledge about the ways classes are defined in terms of features. And what is interesting is to determine whether or to which extent the classifiers that has been learned complies with those prior pieces of knowledge. Okay, those are verification queries. And I will focus only on one of them for time reason, measuring how much classes are close to each other with respect to a specific similarity measure given by what is called as Jacquard index. Okay, so this was the view of XAI queries from the classification side, okay? Explaining, verifying, but we can also view XAI queries from the computation side. And if you had enough time to look at the previous slide to see what was given there, there are listed there a number of problems that are quite different from the point of view here of computation. You have decision problems, you have counting problems, you have enumeration problems, and you have, in general, function problems. Okay, what can be shown is actually that those problems, each of them is NP-hard in the broad sense. Okay, when sigma, the circuit is not restricted, the language is not restricted, or even when sigma actually is given as a CNF formula. Okay, NP-hard in the broad sense just means that if for any of those queries a polynomial time algorithm would exist, we would have P equals NP. And because we have enumeration problems, okay, in the list, for enumeration problems, it assumes that if we add any enumeration algorithm with polynomial delay, we would have P equal NP. Okay, so what we have done is to look for tractability conditions on the language, on the representation language of the circuit, and our technique consisted in abstracting away the language. Okay, we are not going to focus on specific languages, but instead we considered a number of properties given by those queries and transformations so as to actually characterize a wide set of possible languages of interest. Okay, so those queries and transformations are the standard ones considered in the knowledge compilation map. Okay, the map we developed with Anand, my goodness, it was almost 20 years ago. So I guess that Thomas Saiter this morning talked a bit about the knowledge compilation map in his lecture. I'm not going to enter into too many details here. All those queries and transformations are standard one, but optimization is a transformation that has been added a bit later. Actually, the question is to determine whether we can, in polynomial time, given propositional representation is in a specific language, turn it and the linear function over the literals occurring in this representation, turn it into a representation from the same language, okay, such that the model of the output representations are precisely those models minimizing the linear function, okay? And decomposable conjunction is quite simple also, starting with a number of representation, not sharing any variables when you took them pairwise, okay? What you want to do is to make a conjunction of the whole. Is it possible to do it in polynomial time in your representation language? Okay. And so quickly, let me give you a few words about two queries. One about explanation. So this one is about counterfactual explanations or contrastive explanations. Those explanations are expected when the result furnished by the classifier is in some sense surprising. Okay, for instance, for given instance considered at start, you were expecting a grapefruit to be recognized, and in fact it is an apple. Okay, so for instance here, if the fruit, the line here in blue, if the fruit is not sweet, not green, and has a round shape, what you get is a grapefruit, and you would expect an apple. So in that case, you are interested in determining the closest instance, okay, the closest to this one in blue, that would be recognized by the classifier here as a grapefruit, okay? And you can do that, okay, using the queries and the transformation of the list. And more specifically, you can do that whenever your representation language, okay, used to encode sigma satisfies the conditioning transformation, the model enumeration query, and the optimization transformation. Okay?
Sorry,
while in the general case, you cannot do that. Okay? I'm running out of time?
Yeah, I will have to see.
Okay, going to, I'm almost done. Okay, the interesting thing is that the NNF is such a language. Okay, and we can do, okay, we did similar investigations for the other XAI queries. For instance, we can have some prior knowledge or prior beliefs about the proximity between classes. The fact, for instance, that the class of apple is as close to grapefruit as banana is close to grapefruit. Okay, and we can check this by considering similarities. Jacquard similarity between classes is simply given by the ratio between the number of common objects divided by the cardinality of the union, in fact. Okay, so you can, what is interesting here is that you can compute these similarities as soon as your representation language satisfies the conditioning, transformation, and the counting query. Okay, and there exist languages for which compilers exist, are available, so that you can do it in polynomial time. While you cannot do that in polynomial time, in general, the problem is NP-hard. Okay, and this is the last slide. So basically, the results of the paper are summarized here in this slide. Okay, for each query we have identified, you have some sufficient condition for tractability here, given as queries and transformations over Boolean functions, such that if the language into which your encoding is represented satisfies those queries of transformation, then the XAI query is tractable. Okay, and then from those results and previous results about the knowledge compilation map, as a consequence, actually, you can derive a number of languages that could prove interesting for representing such encodings. And thank you.